Problem on LCR circuit. The power factor of this circuit is given by 1 by root R, root 2. Resistance is 10 ohms, inductance is 0.1 Henry. What is the capacitance in this capacitor? Now, as the power factor is given, we know the power factor is nothing but cos phi, which is given by 1 by root 2. So, from basic points, we know that cos phi is the average power consumed by Vrms into Irms. So this can also be written as the average power consumed or true power consumed by, as this is apparent or virtual values, we can write this as apparent power here. Now, what is this true power? What is this apparent power? True power is the power consumed by the resistor. We know that both inductor and capacitor cannot consume any power here, as only resistor is consuming power. So we can write the true power as the power consumed by the resistor. The expression for this one is I square R. And the apparent power is, apparently even this reactors consume some power only for particular time periods. So while explaining about the power, I explained this one in a complete cycle. For half of the cycle, power consumed may be positive and negative. Remaining half of the cycle, power can be positive and negative. So here, that means even this inductor and capacitor consumes power for a particular time period. So this power is called power consumed by the reactance, and apparent power is the sum of the true power plus the reactance power. So I am going to write here, the apparent power is the sum of the true power plus the reactance power, that is power consumed by the reactance of this LCR circuit. So I am going to add these two. This is I square R, this is I square X. So I can write I square into R plus S, or directly I can write this as a Z here. Now if you cancel these two, the power factor of any LCR circuit is given by resistance of the circuit by Z value. So I am going to write this as R by this value root over R square plus, it may be XL minus XC or XC minus XL. So instead of that I am going to write the total reactance as X here. Now the cos phi value is 1 by root 2, which is equal to R by root over R square plus X square. Remember students, this X is not the reactance of inductor or reactance of capacitor. Here X is the sum of these two. But remember, sum is here. We cannot add these two. We should write this as XL minus XC. So instead of XL minus XC, I am going to write X square. Now squaring on both sides, you will get 1 by 2 is equal to R square by R square plus X square. From this by square multiplication, cross multiplication, 2R square is equal to R square plus X square, or R square is equal to X square, R is equal to X. That means for this given problem, the resistance is equal to the combined reactance of inductor and capacitor. So I am going to use this concept here as R is equal to X. We know the R value is equal to 10. So R is equal to XL minus XC, that is 10 is equal to omega L minus 1 by omega C. Now this 10 is equal to omega can be written as 2 pi FL minus 1 by 2 pi FC. And here the voltage applied is given by V is equal to 2 sin 100 pi t. Generally the equation of voltage is given by V is equal to V naught sin omega t. Here omega is equal to 100. So instead of this omega, we can replace this as the value of this one is 100 as well as the value of this one is 100. So 10 is equal to 100 into, what is the self-reluctance of the inductor used here? This is equal to 0.1. So this is 0.1 minus 1 by 100 into the capacitance of the capacitor that we are using in this LCR circuit. So 100 into 0.1 is 10. So this 10 is equal to 10 minus 1 by 100 C. Now this 10 get cancelled. and from this 1 by 100 C will become 0. So capacitance C will become infinite. So that means we need to connect a capacitor whose capacitance is infinite here. But in the options, if it is not given, once again we can write this as R is equal to XL minus XC. In place of this, we can write XC minus XL also. So then this expression will change here. If the option is infinite, then you can go for that option. If infinite is not given, then we can write R is equal to 10. This is 1 by omega C minus omega L. We know the omega value which is equal to 100 here. So this will become 10 into 1 by 100 C minus 100 into L is equal to 0.1. So 10 is equal to 1 by 100 C minus. This is once again 10. If minus comes, this is 10 plus 10. Total it will become 20 is equal to 1 by 100 C. I need capacitance which is equal to 1 by 100 into 20. This is 1 by 2 into 10 power 3. 1 by 2 is 0.5. So this is 0.5 into 10 power minus 3. So this is the option. That means 0.5 millicoulombs. But students, remember, sometimes you may not get this millicoulombs. The option may be given in microcoulombs. Then we can write this as 0.5 millicoulombs, which is equal to 0.5 into 10 power minus 3, 10 power minus 3 by 10 power plus 3 into coulombs. That means I am multiplying this with 10 power minus 3 into 10 power plus 3. Then these two, 10 power 3 by 10 power 3 will become 1. So there is no change in this value. But if you multiply this with 10 power 3, this will become 50 into 500 into 10 power minus 6. The answer may be given in microcoulombs also. Be careful. One inductor resistor R1 connected in series. The power factor of this circuit is 0.6. When a capacitor and another resistor R2 connected in series, power factor is 0.5. But in the same inductor, same capacitor, but these two resistors are connected in series, the power factor is 1. So what is the ratio between R1 and R2? What is the ratio of R1 and R2? So first let me take this concept here. The power factor is given by 0.6. I am going to write this as 6 by 10. So which is equal to, power factor can be written as, just now we solved a problem, R by Z is equal to 6 by 10. This is R by, what is Z here? Root over, this is R1 square plus XL square is equal to 6 by 10. Squaring on both sides you will get R1 square by R1 square plus XL square is equal to 36 by 100. So from this, by cross multiplication, 100 into R1 square is equal 36 R1 square, 36 XL square. 100 minus 36 will be 64 R1 square is equal 36 XL square. So now you can cancel this, 4 9s, 4 16s. So this can be written as 16 R1 square is equal to 9 XL square, or 4 R1 is equal 3 XL. This is equation 1, square root on both sides. Now for the second circuit, I am going to solve this here itself. Power factor cos phi is equal to R by Z, which is equal to 0.5, that you can write 1 by 2. So what is R will I here? Here I can write this as R2 by root over R2 square plus XC square is equal to 1 by 2, squaring on both sides. R2 square by R2 square plus X square is equal to 1 by 4. 4 R2 square is equal to R2 square plus XC square. 3 R2 square is equal to XC square. So here also we can write the relation. This 4R root 3 R2 is equal to XC. This is equation 2. In the third case, when these are connected in series, the power factor is 1. The power factor 1 means this circuit is in resonance. Because power factor value R by Z, Z is equal to, these two must be same. So this must be 0. So reactance is 0 here. So this is in resonance. In resonance we can write XL is equal to XC. Here XL is equal to 4R1 by 3, 4R1 by 3, and XC is equal to root 3R2. So R1 by R2 is equal to, by cross multiplication, 3 root 3 by 4. Is a device used to change the voltage of alternating current source or input voltage. Here a transformer consists mainly soft iron core. Here this is the soft iron core. It may be in rectangular form or square form. This is the soft iron core. We are not using a complete metallic block here. Why? Because already we discussed this in eddy currents. If we use a complete metal blocks, eddy currents will be induced here. This, due to this eddy currents, we may have maximum power loss. To reduce that eddy current loss, we are going to use soft iron core with so many thin blocks here, thin plates. So here one side it is wounded with one coil, copper coil. On the other side we may have copper coil wounded on the other side. So this is called a primary coil and this is called a secondary coil. Now what is the working principle of this transformer? Transformer works on the principle is mutual induction. That means whenever the current through the first primary coil changes, there exists a magnetic field or magnetic flux through this one. When this flux passes to the second coil, if that is also changing through this one, an EMF will be induced between the two ends and the current flows through this one. So this is the mutual induction. So let me connect this to a AC source here. Here when the AC source, we know that the input current varies like this. Whenever there is increase in current, decrease in current, and then in the reverse direction, here the field lines will travel in this direction. Field lines gradually increases, and these field lines, as they are closed lines, this flux will pass through this one also. If the current decreases, it becomes zero, field lines will become zero here, flux will become zero, flux will become zero. That means whenever there is a change in flux in the primary coil, a similar change can be observed in the secondary coil if they are linked such that there is no flux losses. But we know that these lines will not pass through this one. So that's why in modern transformer, both primary as well as secondary coils are wounded on the same core here, such that the entire flux that is passing through the primary coil will pass the second coil. There, the flux change or flux losses can be made zero here if they are wound on the same coil. Now in this case, what we are going to write? Due to the flow of this current in this one, whenever current changes, magnetic field changes. Whenever magnetic field changes, flux through the coil changes. Whenever flux changes, the EMF will be induced here. And due to this one, if they are wound on the same core, then flux through the primary coil is equal to flux through the secondary coil. That means the rate at which the flux changes through the primary coil is equal to the rate at which the flux changes through the secondary coil. So if it is the case, then what is the EMF induced in the primary coil? According to that formula, NP d phi by dt. This is equation 1. So this is the EMF induced in the primary coil. Similarly, what is the EMF induced in the secondary coil? This is Ns, total number of turns in the secondary coil, into d phi by dt. But if there is no flux losses, then we know that flux through the primary coil is equal to secondary coil. Then the rate of change of flux through the primary coil is equal to rate of change of flux through the secondary coil. So these two can be cancelled. Then EP by ES is equal NP by NS. So this is equation 1. After that, if there are no power losses for ideal transformer, power loss can be taken as 0. If power loss is equal to 0 in a transformer, so what we can write? The output power or power through the primary coil is equal to power through the secondary coil. So what is the power in the primary coil? The power in the primary coil is EMF induced or voltage across the primary coil. So as there is no internal resistance, this EMF can be written as VP and this can be written as VS. So we can write VP IP is equal VS IS. So from this, what is VP by VS? Which can be written as IS by IP. So this is equation 2. In the equation 1, VP by Vs is equal to NP by Ns. That means ratio of the voltage across primary and secondary coils is equal to ratio of number of turns in the primary and secondary coils. Similarly, ratio of voltages across the primary and secondary coil is equal to ratio of the currents in the secondary to the primary coil. So here it will be reversed. So if you combine these two, we can write, this is called transformer formula. Voltage across the primary coil by voltage across the second coil is equal. Number of turns in the primary coil by number of turns in the secondary coil is equal. Current through the secondary coil by current through the primary coil. You can write this only for ideal transformer. A transformer in which no power is lost here in this case. Now once again, here if you write this one, NP by NS. NS by NP is also called turns ratio in the transformer. Why? Because in some problems they won't mention which are number of primary turns, which are secondary turns. They will just give NS by NP is equal to 24. So what is the meaning of this one? If turns ratio is given as 24, don't take primary by secondary. Always this is a number of turns secondary by number of turns in the primary only. Now based on this one, based on this number of turns, whenever the number of turns changes, voltage changes as well as current also changes. So by using this turns ratio, we can say, that means we can divide this transformer into two types. One is a step up transformer, the second one is a step down transformer. Step up transformer, second one step down transformer. In step up transformer, up means increases, the voltage across the second coil or secondary coil increases. So here voltage increases, here voltage decreases. As we are discussing about the ideal transformer, power is equal to VI. As the power is constant, there is no loss of power for an ideal transformer. If voltage increases, obviously current will decrease. So step up transformer is a transformer in which the output voltage increases or the output current decreases. What is this step down transformer? A transformer in which the output voltage decreases or the output current increases. Now we know the relation between voltage, current and number of turns. That is, voltage across primary by voltage across secondary is equal. Number of turns in the primary by number of turns in the secondary is equal. Current in the secondary by current in the primary. So this is the relation between voltage, number of turns and current. Here in step up transformer, voltage increases. So the secondary voltage increases, means number of turns in the secondary must be more. If you consider these two, as this value is more, number of turns in the secondary coil must be more. So while drawing the diagram, in this case, if it is the core, the number of turns in the secondary must be more. So here number of turns in the secondary are more, but number of turns in the primary coil are less. So from this we can write NP less than NS. So how to define this step up transformer? A transformer in which the output voltage is greater than the input voltage, the transformer in which the output current is less than the input current, or the number of turns in the secondary are more than number of turns in the primary. Similarly, in case of step down transformer, voltage will be less in the secondary, current in the secondary will be more. So from this same concept, as the voltage at the secondary is less, the number of turns the secondary must be less. So NP greater than NS. So in this case, if you take this transformer here, this is the core of the transformer. So here the number of turns in the secondary are less, but the number of turns in the primary are more. So NP greater than NS. Due to less number of turns, the flux linked with the secondary coil will be less. So flux linked with the second coil will be NS into d phi by dt. And as it is less, the output of the secondary coil will be less, and as a result voltage in the second coil will be less. As a result, the current increases. So this is how we can divide this transformer into step up and step down transformer. Suppose instead of this ideal transformer, let us say in general for a given transformer, which is not ideal. This is not ideal transformer. This is not ideal transformer. Here what happens? The output power always less than the input power. So the efficiency of an ordinary transformer is the output power by the input power, which is going by what is output power? Power in the secondary coil by power in the primary coil, which is equal to voltage across secondary by current in the secondary coil by voltage across primary coil by current in the primary coil. So this is the expression for efficiency. The efficiency actually measured in terms of percentage. So this can also be written as VSIS by VPIP into 100. This is efficiency in percentage. Admittance. Admittance generally denoted the letter A, which is equal to 1 by Z. That is called 1 by impedance. In DC circuits, conductance is the reciprocal of resistance. So conductance is the reciprocal of resistance. So this is the expression for conductance, and it is measured in mho. Resistance is measured in ohm and conductance is measured in mho. Similarly for AC circuits, because here we may have pure capacitor, pure inductor, pure resistor, or LC circuit, or CR circuit, or LCR circuit also. Different circuits are possible here. So for a single circuit, this we call it as a reactance XC. This is XL. This is resistance. Here the reactance is sum of these two, that is XC square plus XL square. Here Z is equal to root over, this is XC square plus R square. Here Z is equal to root over XL square plus XC, XL minus XC whole square plus R square. These are the different opposition offered by the components of AC circuit for the flow of AC current. The reciprocal of is this one, this one, this one, or even this one is called admittance, and this is also measured in mho only, just like this DC circuits. Choke coil, also known as ballast. You might have seen these fluorescent tubes. We call it as generally tube lights. In these tube lights, this is the holder that is used to keep this tube light in the required position, and you can see a small box which is provided here. So this is a small box which is provided here is called a choke coil. So what is the use of choke coil and why it is used? Generally, if you take these fluorescent tubes or mercury tubes, if you connect them directly to a AC source, what happens? Let us say this is a choke coil, this is a tube light here. If this tube light is directly connected to a AC source, If the applied voltage is equal to V is equal to V naught sine omega t, the voltage across this fluorescent tube will be equal to the applied voltage, and this heavy voltage may damage these fluorescent tubes. But to avoid this damage, what we are going to do, here we are going to connect one inductor in series to this tube light. This bulb will have some resistance, and we will connect one inductor here. This inductor coil, which is used in series with a mercury bulb or fluorescent tube, is called choke coil. So when this choke coil is connected in series to the resistor, then the self-inductance of this choke coil is L. It is connected to the AC source of potential V is equal to V naught sine omega t. So in this case, what is the potential drop across this one? As these two are connected in series, the same current will flow through the circuit. So now we are going to write XL is equal to omega L, which is equal to 2 pi FL. So this is XL. Similarly, what is the total impedance of this circuit? The total impedance of this circuit is root over XL square plus R square. In this case, without choke coil, if you connect this to the circuit, without choke coil, what happens to the current through this circuit? Current I is equal to V by R only. But with the choke coil, so here with the choke coil, this is the bulb here, this is the tube, or we can write. Then what is the current through this one? The same voltage by, now this will become root over R square plus XL is nothing but omega L of the choke coil here, self-inductance of the choke coil. You can see here denominator is only R, but here denominator is R square plus something. That means this value is bigger than this. As this value increases, less current will flow through this one. When less current is passing through this tube will not be damaged. So that is why to send the less current through this tube, we are connecting an inductor here. And you may have a doubt, instead of sending this, instead of using this choke coil here, why can't we use a resistor here? What happens? Why we are not using another resistor here? If it is R, why we cannot R dash? Why we cannot use another resistor? If you use one more resistor here, then what happens? This resistor would consume some more power, and power to the bulb will be reduced. Here our main dream is, we want to give the complete power to the bulb, and no power should be consumed by this one. That's why here, as we know that power consumed by inductor is 0. So as it is 0, so if you use this one, the current will decrease and the power consumed by tube light remains as it is. That's why we need to use compulsory a choke coil in series with a tube light. Volt 100 watts lamp is run on a 100 volt 50 Hz AC mains. Calculate the inductance of the choke coil required. So this is a lamp here, which is a rating of 50 volts and 100 watts. And it is connected to an AC source here, whose potential is 100 volts. You can see the input voltage is 100 volts, but the voltage required for this bulb to work is only 50 volts. So now, instead of AC source, so let me take one DC source here. This is a bulb 50 volts, and let us say this is connected to a battery here. What is the resistance required for this bulb to work? As it is 100 volts, here 50 volts will drop. What must be the voltage drop across this resistor? This must be 50 volts. Because in DC circuit, the total voltage of the battery is equal to voltage drop across the resistor plus voltage drop across the bulb. So we can add this voltage plus this voltage, which gives this voltage. So this is 100. Voltage across resistor, which is unknown here, but in the problem it is given as voltage across bulb is 50. So this value will become 50. Then by using this power here, as it is 10 watts, we know that power P is equal to VI. 10 watts is equal to 50 into I. Cancel I is equal to 1 by 5. So the current that is passing through the bulb is 1 by 5 amperes. So what is the current through this resistor? This is also 1 by 5 ampere. So for this resistor, V is equal to IR, voltage drop is 50, current to 1 by 5, R is unknown. So R is equal to 250 ohms. This is how you can solve in case of a DC source, because total voltage across the two terminals of the battery must be equal to voltage across the bulb plus voltage across the resistor. But in this case, I need to connect an inductor here, choke coil here, so that the total power will be consumed by this one only. Now the choke coil, what is the inductance of this choke coil? So in this case, for this, I cannot write voltage here is equal to this voltage plus this voltage. Here what we can write? First, for bulb, what are the given values? As we discussed earlier, what are the values that are given without any name in these problems? These are all called root mean square values, RMS values or virtual values. So here, what is the virtual voltage that we are supplying here? 100 volts. So for bulb, the voltage is 50 volts, the power is 100 watts. So we know that power P is equal to VI. So current through the bulb is given by P by V, which is equal to 10 by 50, which is equal to 1 by 5. That means the current that is passing through the bulb will be 1 by 5. If I know this value, we can find out the current through this one. From this, what is the resistance of the bulb? We know from Ohm's law, R is equal to V by I, which is equal to 50 by 1 by 5. So this is 250 ohms. This is the resistance of this bulb. So after getting this resistance, now what is the total EVRMS for source here? For the source, what is VRMS? This is given as 100 volts. So how much current is sending by this source here? As these two are connected in series, we know the current through this one is equal to 1 by 5 amperes. Current through inductor must be also 1 by 5 amperes. So current from the source must be 1 by 5 amperes. So we can write IRMS is equal to 1 by 5 amperes. So based on these two, the impedance of this circuit, entire circuit is given by VRMS value by IRMS value. This is 100 by 1 by 5, which is equal to 500 ohms. This is the impedance of this entire circuit. We know that the impedance is equal to Z is equal to root over R square plus XL minus this XC whole square. Z is equal to root over R square plus XL minus XC. Here there is no capacitor. That's why we can write XL whole square. What is Z? The impedance of the circuit, just now we found this as 500. What is R? The resistance of the bulb, which is we obtained here. This is 250 ohms. So this is 250 ohms plus XL square. So squaring on both sides will get 5 5s are 25 into 10 power 4 is equal. This will be 250 square plus XL square. So this is 25 into 10 power 4 is equal 25. 25s are 625. So this is 625 into 10 power 2 or 6.25 into 10 power 4 plus XL square. You can bring this one this side. This 25 minus 625, 6.25. 10 power 4 is common. So this is 10 power 4 is common. 25 minus 5 is 20. So this is 18.75 into 10 power 4, which is equal to XL whole square. So from this we can write XL is equal, the inductance of this one is L and the reactance of this inductor is XL, which is equal to 18.75 under root into 10 square. But we don't want the reactance here, we need the inductance here, which is equal to omega L. This is equal to root 18.75 into 10 square. Here L is, omega is given by, here what is the frequency of the AC source that is given here? 50 Hz frequency. So omega is equal to 2 pi f. So you can write 2 pi into 50 into L is equal root to 18.75 into 10 square. So from this we can write the L value, self-inductance of this choke coil required for this bulb to work in its given value is equal to root over 18.75 into 10 square by, this is 2 pi, this is 100 pi. You can cancel this 100 and 100 here. The self-inductance of this coil will be given by root 18.75 by pi value 3.14. You can see this value root 18, root 16 is 4, this is slightly more than 4, this is nearly 3. So this is around 4 by 3, around 1.3. So we have to select the nearest value by checking the options given. So this is around 1.38 Henry here.